right, guys, thank you for joining us for the April edition of Scibar Online. In tonight's talk, we're going to explore how light particles and basic principles of quantum physics can facilitate the secure exchange of information. Now, if you're like me and the words quantum physics makes you a little nervous, not to worry. Professor Rachel Oliver is here to explain it all tonight. She's the Professor of Material Science at Cambridge University and is the Director of the Cambridge Centre for Gallium Nitride. So over to you, Rachel.
Oh, thank you. Right, hopefully I'm just going to make my slides share and it will all go brilliantly. Okay. Could somebody unmute themselves and tell me if they can see the slides?
Perfect.
I hope you can see me as well, and it's nice to be able to see some of you, so hello. So do not panic, because although I'm going to be talking about some quantum physics type stuff, I'm not actually a quantum physicist myself. I'm a materials scientist. I call it the kind of grubby end of this sort of work. So I work on the materials that will enable these sorts of technologies in the future. And that means that I have to think quite hard to be able to understand the more quantum aspects and where this is going. And hopefully, therefore, I can give you some of the thinking that's helped me understand it and it won't be too confusing. So I've called this talk Secrets and Lights, and it's about how we might be able to use light to communicate more securely. If I can make the slides go forward, I'm going to answer, hopefully, a few questions. Now, to understand this idea about doing secure communication using light, the first question we need an answer to is, what is light anyway? And that may seem like an obvious one, but it's a simple question which turns out to have quite a complicated answer. Then I'm going to think about how we can use light for secure communications and why we need new ways to communicate securely. So let's crack on with what is light. So I know we've got a school science teacher listening, so I'm actually thinking back now to my very first physics lesson when I must have been about 12. And in my very, very first physics lesson, a gentleman called Mr. Pettigrew, who was my first physics teacher, told us that light is a ray which travels in straight lines. Now, if I was doing this talk in person, at this point I'd have a laser pointer and some talcum powder, and I would do exactly the experiment he did for us, which is to shine the laser across the room, sprinkle the talcum powder in through the beam, and you can see the beam and you can see it as a beautiful straight line, just like you can see these beautiful straight sunbeams in this photograph. And that's actually a really useful picture of light, and it allows you to do all sorts of ray optics types of things and understand a lot of useful things about light. But it turns out to be quite an incomplete picture of light. So I went on learning physics at school, and eventually I learned a new answer to the question, what is light? Oh, but first, I did promise stormtroopers. This is my kind of favourite light is a ray picture. This is kind of embodies light as a ray to me, these stormtroopers with their blasters blasting these rays of light all over the place. I'm not really quite sure what's meant to be happening, because you can the rays actually move quite slowly relative to the speed of light. But yeah, that's kind of light as a ray. As I say, I went on through school and learned new pictures of what light is. And the next picture I learned about what light is this idea that light is a wave. Now, I guess everyone should be pretty familiar with water waves at the seaside or wherever. And we know that waves behave in certain ways. So you can see here that in this little sort of rock pool, let's see if I can have a pointer. Then we've got different waves, and sometimes where they meet each other, the troughs of the waves meet the troughs of other waves, and the crests meet crests, and it ends up with a bigger wave pattern. And sometimes troughs meet crests and crests meet troughs, and the waves kind of cancel out. And we can do that in a much more controlled fashion with water waves. So this is now two controlled, beautiful circular water waves. So each of these points here and here basically has a little hammer that's tapping on the surface of the water, and it's creating a water wave that comes out in a circle from that point. And where the circles of wave overlap, okay, if you've got the trough of the wave meeting the crest of the other wave, the two cancel out and there's nothing. And in places, the troughs add to troughs and the crests add to crests, and you get a really strong wave. And you can see this kind of pattern of big waves and little waves all over this tank. And we talk about that as the interference between the waves. And it's something that you can literally see in a puddle if you drop a couple of pebbles into it. And that's a familiar known property of waves. So if light is a wave, it should do this. And actually, it was shown a couple of hundred years ago that by, I think it was Young, that even using sunlight, you can actually prove this. So you can create a light source from sunlight using a slit that creates this kind of circular wavefront from a beam of sunlight. And if you then, in order to create two wave sources, just put two slits in front of it, where those two light waves meet one another, the troughs add to the troughs and make bright regions, intense regions of light, or the troughs cancel out with the peaks, and then you have a dark region, and you get the same interference pattern you might get in water, except in light and dark on a screen. Again, if I were with you in person, I would do this as an experiment on a screen. If you really feel that you have missed out very badly on the experience of seeing me produce a diffraction pattern or an interference pattern from light, this is actually an experiment you can do at home if you have a standard laser pointer, which people have for giving talks and stuff, and a Nick comb. Nick combs actually work really well as ways of creating wave fronts and creating diffraction patterns. So a metal Nick comb that you might choose to remove nasty insects from a child's hair with is also a way to do your own double slit or multiple slit experiment and create your own interference pattern. Okay, so I learnt a picture of light as a wave, and you'd think at that point we'd be happy with our pictures of light, but in fact there's another picture of what light is, which is that light is a stream of particles, and we call those particles photons, where a photon is a quantum of light, by which I mean the smallest amount of light that can possibly exist and still be light. Now, as I say, if we were in a pub and I were with you in person, I could do a pretty simple experiment that showed you that light is a wave, okay? I will talk in a minute about the experiment we can do to show that light is a particle, but that's a much more difficult experiment and I couldn't easily do it on a tabletop in a pub. The person who first proposed this was Albert Einstein, and actually, this is a little known historical fact, Einstein actually won his Nobel Prize for his work on something called the photoelectric effect, which he thought through and understood as a proof of the particle nature of light. Everybody was kind of a bit freaked out by general relativity and special relativity and other fancy Einstein things that he came up with. But the particle nature of light is what he actually got the Nobel Prize for. So, you know, kind of trust me, Einstein was quite clever. Light is definitely a particle as well as a wave. So this is getting to sound a bit weird, okay? Because I've just said light is a particle and then I've said that light is a wave, and these two things seem to be contradictory. Would anybody like to unmute and read the text in the white box on the screen for me? Don't all shout at once.
I feel like I'm setting myself up to sound like an idiot here, but I'm going to say light is a wave.
Okay, and what do you think it says now? Does it look at anything different to anybody?
Oh yeah, light is a particle. Very clever.
Yeah. I saw particle and then wave.
I don't really mind which way around people see it. So yeah, this is just a trick, an optical illusion, basically. The point of it is, though, is that it's not that light is a particle or a wave. It doesn't sort of switch between them. Light is always both a particle and a wave, all at the same time. And that is because quantum physics is really weird. And we have to kind of live with that duality, that fact that light is both a particle and a wave, and also looks like a ray that travels in straight lines, to be frank. And all these things are true simultaneously because quantum particles are capable of being deeply odd. Okay, So I said showing that light is a particle was a tricky experiment and not one that I do on a tabletop in a pub. The experiment itself that we use for this, that is my kind of favorite proof of the particle nature of light and is also really useful looking at some of the light sources I work with, is called the Hanbury, Brown and Twist experiment. And it's this setup here. Now I'm going to explain it to you. And if I were doing it in person, we would do a demonstration whereby we would prove that a tennis ball is a particle using a kind of analog of the Hanbury, Brown and Twist experiment. Because I can't do that with you and lots of tennis balls. Instead, I have how to show that a baseball is a particle as a little animation here, okay? So in my sort of schematic of my lab experiment, I've got a light source, I've got a beam splitter, and I've got 2 detectors, okay? And I've got the same setup, except here, my light source is my pitcher. He's the guy who's going to throw my baseball. And I've got 3 catchers. My purple catcher here is the beam splitter. And my 2 detectors are my green catchers. And my beam splitter is going to catch the ball and then going to take a random decision. It's going to be a 50-50 chance whether they throw it to the detector here or the detector here, okay? When I actually made this little animation I'm about to show you, it actually was done with random numbers. So if I recorded a different, like, couple of minutes of it, we'd see completely different things. But we'll now have a look at the version we've got here, if I can make it play. Okay, so I'm going to play this, okay? So here comes my light source throwing my photon or my baseball to my beam splitter. And we can see that the beam splitter at random may throw it one way or may throw it the other. But that baseball can only go down one path. So as long as my light source, my pitcher, only throws one baseball at once, then we never get a baseball arriving at the top detector and one at the side detector at the same time. And we can measure how much time it takes between a baseball arriving here and a baseball arriving here. That's the time interval we measure. And sometimes it may be quite a long time between one arriving here and one arriving here, because sometimes several go that side. That's just how it is. Sometimes when you throw a coin, you get heads lots of times. But there's always some finite time between the baseball arriving at one detector and the baseball arriving at the other detector. Okay, and that's pretty obvious with baseballs. But if we have as our light source a very well controlled light source called a single photon source, which gives you exactly and only one photon on demand, then that photon should go to my beam splitter and then be able to go to one detector or the other. But if it's an indivisible quantum particle, it can't go both ways. It has to go this way or this way. And if we can measure the time between the photon arriving here and the photon arriving here, if we've got a beam of single indivisible quantum particles, that time should never be 0, okay? How we do that? Well, we draw a graph. This is sort of how it should look in theory. What I've got here are coincidences up the side and time delay along the bottom. So this big dip at time equals 0, right here, okay? That dip is telling us that we never have a photon arrive at one detector and at the other detector at the same time. Because a single photon, which is an indivisible quantum particle of light, it can't do that, it can't go both ways. But it would be absolutely fine for my baseball pitcher to throw a ball to one and then 3 seconds later throw the ball to the other catcher. And similarly, it's absolutely fine that a photon arrives at one detector and then 20 nanoseconds later arrives at the other, because that's 2 separate photons arriving at 2 separate times. Similarly, you could have had a photon having arrived 20 nanoseconds before and then one arriving at the time we're calling 0. All in all, then, you get this dip in the curve. So lots of times the gap between the arrivals of the photons at the 2 detectors is 20 nanoseconds or 30 nanoseconds or 17 nanoseconds or whatever, but it's never 0. And this dip down towards 0 only happens because light is particle-like, because it reaches a point where you can't split it any further. Whereas you think of a wave as just always being able to split in two and being diverted one way and then diverted the other. Okay, so that's how it looks in theory. This is just an example of the experimental data set, which has this nice clear dip, okay, except it's a whole lot noisier because real data in the real world is often noisy. My data doesn't quite look like this. We use a pulse mode variation of the setup. All I mean by that is that rather than kind of putting our finger on the on button and getting a continual stream of single photons, one after another at fairly random intervals, we have a device where we put our finger on the on button literally every 20 nanoseconds, and hopefully we get one photon for every press of the button. So you get a photon every 20 nanoseconds, and you get in your data a stream of pulses with a missing pulse at this time of 0. And all that's saying is, again, never having a photon arriving at both detectors simultaneously, but you can have one arrive at the first detector and one 20 nanoseconds after. You can have one arrive at the first detector and then another at the other detector 40 nanoseconds after. Or there could have been one arrive 20 nanoseconds before. So all the pulses are present apart from this missing pulse at time equals 0. So this is now data from a device that I made, which does indeed give you this stream of single photons that you need to do this experiment. A normal light source you've got, which is in red, which isn't a single photon source, gives you many, many photons each time you press the button and doesn't have this dip because some photons are available to go down one path, some photons can go down the other. It's only when you get to this light source that is only giving you one at a time, so it has to choose which path it can go down. There aren't any spares to pop off down the other way. Then you get this dip. So 1, 2 slightly noisy peaks, a dip, and 2 more slightly noisy peaks. So that's the first single photon source that I ever made in about 2007. And it was also the first in the world in the type of materials that I work in. Okay, so what does that device look like? How do we get this stream of single photons? Well, I'm going to start with how you don't get a stream of single photons, okay? The structure I've got here is the structure of a light emitting diode. Now, I work in a material called gallium nitride, which is really famous for being used in light emitting diodes. In 2014, 3 Japanese gentlemen, Nakamura, Akasaki and Amano, got the Nobel Prize in Physics for having invented gallium nitride based light emitting diodes. And these are the light emitting diodes that are inside LED light bulbs that you might be buying to be like low energy light bulbs to use in your house and reduce your electricity bills. Okay. And what these have, they are made mostly of gallium nitride, and they have 2 different sorts of gallium nitride. In p-type gallium nitride, the electricity is carried by positive charge carriers. And in n-type gallium nitride, electricity is carried by negative charge carriers. And we push the negatives and the positives together in this region here that I've got labeled as quantum wells. Now, what these quantum wells are is they're very, very thin layers of another material called indium gallium nitride. That just means we've mixed up indium nitride and gallium nitride, 2 different nitride compounds, to make something in between, okay? And the indium gallium nitride makes what are basically little traps for the negative and positive charge carriers. So the negative and positive charge carriers fall into these traps in these thin layers of indium gallium nitride. And the indium gallium nitride is a bit like the filling in a sandwich. So if you imagine this as kind of a multi-layer ham sandwich, the gallium nitride is the bread and the indium gallium nitride is the filling. And the charge gets trapped in the, I don't know, I put ham in my sandwiches. So the ham layer in the sandwich is where the positives and negatives all get trapped. And then where they're trapped, they combine with one another and we get light out, okay? So that's how a light emitting diode works. We inject positive and negative charges. We have these thin layers where we can trap them. And when they're trapped together, they tend to meet one another, combine, and out comes light. Now, the problem with that, if I want single photons, is that in these thin layers, although they're very, very thin, I can actually trap lots and lots and lots of positive and negative charges. And when all those positive and negative charges find one another, they combine with one another and out come lots of photons. So this isn't a single photon source, it's a multiple photon source. And for what you want an LED for, that's grand, because you don't want your LED bulb like in your ceiling of your living room only giving you one photon at a time, because that's very little light and it wouldn't be very bright and you wouldn't be able to see your way across the room or read a book or whatever else you might want to do with your lights. So if we want to make single photons, we have to take out these layers and replace them with something else. And what we replace them with is just individual, very, very tiny crystals, again, of indium gallium nitride, but are so small, there's only space inside them to trap one positive charge and one negative charge at any given time. And those two charges combine with one another and give us exactly one photon. And it's just in the nature of these very tiny crystals that they have to then contain just their one positive and one negative, and then you have to put another set of charge in before you can get another photon out, and then another pair of charges in before you can get another photon out, just because they're so small and there's nowhere to put any more charge. So this then starts to look like something that may be familiar to some of you. You might at some point, and I'm sure a school science teacher certainly, have drawn pictures like this of the hydrogen atom, which have a ground state and then an excited state, so we might call them an S and a P orbital. And actually, a single hydrogen atom can totally be a single photon source. It has one electron orbiting around its nucleus, and that electron can go from the ground state into an excited state, and if it drops back down, you get one photon out. And then if you wanted another photon out, you'd need to provide some energy to shove the electron back up into the excited state. So you'd only be able to get one photon at a time. And the ways that electrons behave inside very tiny crystals actually looks a lot like the ways electrons behave in the hydrogen atom. So we can calculate what is essentially the ground state of the quantum dot, which is the electron kind of sitting somewhere in a kind of oval puddle here. And if we move it into a more excited state, we get a kind of two-lobed puddle instead, just like this p orbital picture of the hydrogen atom. And we do call these tiny crystals artificial atoms because they behave in terms of their electrical and optical properties actually really quite a lot like atoms. But isolating single atoms is really a nuisance. It's difficult to do. But these tiny little crystals I can actually include in an LED that is otherwise almost identical in structure to the one you might have in a light bulb in your house. So this is something that is manageable and usable in a real world context. What do I mean by very tiny? This one here from this particular paper that I just thought was a nice picture, so I borrowed, is about 6 nanometers tall and a few tens of nanometers across, where a nanometer is a billionth of a meter or 1/1,000,000th of a millimeter. Okay. So these are my actual quantum dots, my actual tiny crystals in indium gallium nitride that I make. These are kind of later iterations than the ones I was showing data from earlier. And we're looking at the bright blobs in this picture. My scale bar here is 200 nanometers. So again, a few 10 nanometers across and maybe a couple of nanometers tall, these structures. This is just kind of looking at the quantum dots when I've deliberately grown them on the surface of a crystal so we can see them. But actually, I grow them and then make process devices where they're inside these pillar structures. The job of the pillars is firstly to just kind of by random chance, we form pillars and most of them only contain one of these little tiny crystals because they're fairly small and fairly sparse. And that means that we can isolate the emission from just one, not have lots, which is important for getting single photons. And also their shape is intended to help channel the light out into our detection system. So with that single photon source, here's my theoretical picture of what my data should look like. In fact, in pulse mode, because that's how we do our experiments. And this is my real data, okay? And we can see we have pulse, 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 and then a dip, and quite a nice clear dip, and then more pulses. But you can see it's not quite like this. So ideally, this dip really should be going down to 0, and we've got some signal in the dip in this case. That's because my device isn't perfect. There are other sources of light emission that's light emission at the same color, which is like contaminating my device. So one of the research problems I work on is trying to clean up these sources so they don't have spare photons that aren't part of our desired single photon stream. I'm showing you this particular device because it's a special one. This data is from it working at 4.7 Kelvin. So that's nearly minus 270 degrees C, really, really cold. That's a temperature we access using liquid helium. And if you are going to be using a single photon source in any kind of technology, you don't necessarily want liquid helium because it's quite difficult to work with. I know of ideas for using single photon sources in like mobile phones and that kind of thing. And you do not want to have a liquid helium dewar in your pocket alongside your mobile phone. That just is not going to work for you. So what's special about this device is it still works at 220 Kelvin, which is more like minus 50-ish degrees C, which still sounds pretty cold, but there are ways of doing cooling on a chip if you are above 200 Kelvin, which means that you can do your cooling in a way that is actually completely invisible to the user. The best devices using these types of materials actually do now work at room temperature. They're best in terms of temperature performance. They have a few other disadvantages. And the other thing that's special about this device is that the photons, the light it gives out, is polarized. What do I mean by polarized? Well, I guess quite likely you've got like polarizing sunglasses and that kind of thing. Interesting. We've been talking totally up till now about light as a particle. We've had our particle, which goes to the beam splitter and can only go both ways. But here we are back with light as a wave. Because if we unpack light a bit more, we don't just call it a wave, we call it an electromagnetic wave. And in a wave, we need something to be going up and down, up and down, up and down. That's what waves do. And the thing that's going up and down here is actually an electric field, okay? And in polarized light, that electric field is only going up and down in one direction. Unpolarized light, like sunlight, you'd have it propagating forwards along the back line, moving forwards along the black line. But the actual electric field could go up and down, or it could go side to side, or somewhere in between. It would be at all these different angles. But once it's been through a polarizing filter, basically your polarizing sunglasses, that pretty much does it, then the electric field only goes in one direction. And that's interesting. That's something that my single photon emitting light devices provide, is light that always points with its electric field in the same way. And we'll see a bit later why that might be important. Just to kind of put it in context, lots of people make these kinds of devices using lots of different materials. And we drew this graph kind of comparing our device to other people's devices. And quite a lot of people can make polarized single photon emitters. And those polarized single photon emitters generally work at up to about 100 Kelvin, so minus 170 degrees C. And quite a lot of people can make devices that are above the on-chip cooling limit, which is somewhere around 200 Kelvin. But ours, at least at the time we wrote this, and I think still, is the only device that is both polarized and also works at reasonable temperatures. So that's kind of why that device is exciting. What you might want to ask, having heard all that though, is why do I care? What on earth are you going to do with this light source that only gives you one and only one and precisely one photon at a time? So I suggest we have a break now. And when we come back, it's going to get a bit more quantum, and I'm going to tell you why you might want one of these single photon sources. And that's where we're going to hit using these in secure communication. Okay, so break time. Recharge your glasses, people. Okay, so as I promised before the break, we are now going to ask what use is a single photon source. You know, I've talked a little bit about what's special about the ones that I make and why they are interesting and what I'm trying to improve about them. But so far, I've mostly told you that they make a pretty useless light bulb. So what use can we make from them? So to understand that, I'm going to need to tell you a little bit about cryptography, about how we exchange information securely. Okay. Now, when we talk about cryptography, I guess the people who do the mathematics of cryptography, and this did start off very much as a mathematical field, to start with, I think they called their people who are exchanging secret information A and B. And then they decided that was boring. So always in cryptography, information is being shared between Alice and Bob. Okay, so I have Alice and Bob in my pictures, and then the person who's trying to steal their secret information is Eve, and Eve is the evil eavesdropper. Okay, as I say, probably started off as A, B, and E, but now we have Alice and Bob and Eve throughout all the cryptography and quantum cryptography papers and generally the literature. So that's what we're going to go with. So Alice and Bob are trying to share some secrets. How might they do that? Well, this is the RSA algorithm. The RSA algorithm was developed by 3 people whose names begin indeed with the letters R, S, and A, and I can never remember any of them. I'm sorry about that. They came up with this way of exchanging information, which is actually how most of our secret or sensitive information is exchanged at the moment. And it's based on this idea that factorizing the product of 2 large prime numbers is very difficult. By which I mean that if you have 2 very large prime numbers and you multiply them together, and then you give somebody that number, which is the answer, it's difficult to figure out what your 2 starting numbers actually were. Okay, so in this bit of the talk, I'm going to talk a lot about keys, and occasionally I am going to draw them as like door keys. When I'm talking about a key, though, what I really mean is a really big number. And in general, what I really mean is a big binary number. So just in 1s and 0s, not using any other digits. So Bob is going to take the product of 2 really big prime numbers. He's going to multiply 2 really big prime numbers together. And he's going to calculate using that product 2 other numbers, which are called the public key and the private key. Only Bob holds on to the private key, but he can send the public key to Alice, and Alice can use that public key to encrypt her message so it's no longer readable. And then she sends it across to Bob, and Bob uses the private key to decrypt it. Now, this is a bit like a postbox, okay? So if you write a letter and take it to a little post box like this, and you stick your letter in through the flap, it's kind of gone. And the only person who can then get at your letter should be the postman, who has the private key. So it's like you've done your encryption, you've stuck it through the flap, and then the postman comes away and comes along and he can do the decryption because he holds the key that opens the little door. Okay, so you don't need to know a lot more about RSA, except that it depends on this multiplying 2 really big prime numbers together and then being difficult to get back to the original numbers. So the question is RSA as a way of keeping our information safe? Well, at the moment, yeah, it's very safe. It's brilliant. But the problem is it's not what we call mathematically provably secure. Okay, we don't currently have a mathematical trick that will allow you to break RSA quickly. But we can't prove that someone isn't going to come up with one, that some very bright person isn't sat, I don't know, in a cold garret in Cambridge right now pondering prime numbers and isn't just going to go, aha, and find a trick which breaks this way of doing code. This book here is from the Millennium series. So I don't know if any of you read the book, The Girl with the Dragon Tattoo. Okay, so that was meant to be a series of about 10 books, and the guy Stieg Larsson who was writing them died after the 3rd one, which is very unfortunate because they were really good books. Somebody else who's, in my opinion, not as good, David Lagerkrantz, has taken over and written a few more. And in this one, The Girl in the Spider's Web, the plot swings on Lisbeth Salander, the main character, being able to do some very clever maths, which in one very specific instance undoes an RSA algorithm. And there are mathematical tricks that under some very specific circumstances already, if you get unlucky, make RSA breakable. So what I would say about RSA is it's not very future-proof, because some clever mathematician might just come along and crack it open any time. The thing that makes it really not future-proof, though, is this article about something that says Peter Shor's algorithm of a theoretical computer dooms RSA to failure. There's going to be new computers which break RSA. So these new computers that are coming along are going to break this way of doing secure communication. I said I was going to be clear, didn't I? And I've been talking about Shor's algorithm and theoretical computers. What is all that about? Well, it's about quantum computing. And I don't want to spend a lot of this evening talking about quantum computing. This is somewhere where the quantum physics does get quite hairy. A way of thinking about it is that a quantum computer, for a problem where you might have to go one after another through many possible answers, looking for the one answer that works to be the answer to your problem, you can think about it that a quantum computer can look at all of those answers at once by doing what's called superposition, like putting them all one on top of the other, and then can bring it down to which of those many answers is the most likely, whilst looking at them all simultaneously rather than looking at them one and then the next and then the next. That is, if I'm honest, not a very good picture of quantum computing. It's exactly the one that is used in the popular press all the time, and it's a little bit inaccurate, but it's as best as we can easily do without a lot of horrible mathematics. So let's stick with it. It's a way of doing computing by looking at all the answers simultaneously, and the most likely one drops out at the end. And quantum computing is a major, enormous research effort all around the world at the moment. This is the IBM quantum computer. It can work with 50 qubits of data, 50 quantum bits. Okay, and the thing I love about the IBM quantum computer, quite apart from the fact that it's just kind of gorgeous. I mean, isn't that a pretty object? Anyway, but apart from the fact that it's very pretty, the thing I love about the IBM quantum computer is you can actually apply, anybody in the world who feels like it can apply to have some time to run quantum algorithms on the IBM quantum computer and try out their quantum concepts. One of the things that quantum computers are really good at is modeling quantum systems. So it lets the people who are working on quantum computers figure out how to make better quantum computers by using the quantum computer. Is it going to break RSA though? No, it's not. Because we think you would need a 20 million qubit quantum computer to break RSA, and this one's got 50. So we're still quite a long way off the pace. But it's definitely progress in the right direction. Okay, so that's RSA, which I've said may not be a very secure way of exchanging information in the future. Now I'm going to tell you about something that actually is secure, okay? This is something called the one-time pad, and you'll be pleased to hear this is really quite a simple way of doing cryptography. Basically, Alice has a message that she wants to send to Bob, and Alice and Bob both have a secret key. In fact, if they're going to chat with each other regularly, sending secrets this way, they need a whole supply of secret keys for each of them, because each secret key can only be used the once. Okay, this takes her message, which in my picture is just like alternating ones and zeros. And her secret key is a binary random number, which is as long as her message. It has the same number of ones and zeros as the message. And all she does is adds the key to the message. Now you're going to look at this and think Rachel can't add up, because I'm doing 1 add 1 here and getting 0. Okay, but we're in binary. So this is 1 add 1 is 1 0. And in this form of addition, for this encryption only, we just lose the carry. Okay, so 1 add 1 is 1 0, and we ignore the 1. We just keep the 0. 0 add 0 is 0. 1 add 0 is 1. We just add it on that kind of way. And then we've got our encrypted message, which is really now just a binary string of random numbers. And the encrypted message gets sent from Alice to Bob. And all Bob does is add the key back onto the encrypted message. 1 add 0 is 1, 0 add 0 is 0, etc. And he gets the original message back. And as long as they only use that key the once, this is unbreakable. You can't extract the message from it. If we look at this £20 note, which has been turned into a binary image, and it's then had a binary random number added to it, you just have random noise. There's nothing that you can see of, like the 20 or the dude with the big mustache or anything here. You've just got like a television that's not properly tuned, and that's it. So the one-time pad, as long as you only use each key once, is properly and mathematically secure. Okay, we can show it can't be beaten using the maths. But I've just kind of moved the problem. What we had before was Bob and Alice with a secret message they wanted to send to one another, and somebody trying to eavesdrop so they couldn't send the secret message. Now they've got to have a key the same length as the message for every time they want to send a secret message. So now the problem is, how do they send the keys to one another without the eavesdropper stealing the key? And the one-time pad is something that's used in communications. It's something more than anything that's used in espionage. It's actually something that was used in the Second World War as an encryption technology. It's very, very secure as long as your people have their supply of secret keys. If they start having to exchange things, it all gets a bit spy movie. You know, I will leave the secret keys in the third hymn book from the back of the cathedral at 4 p.m. on Sunday afternoon type job. What we need is a way to exchange the secret keys securely. And that's what quantum cryptography is going to do for us. So as you listen to the rest of this, the one thing I want you to remember is that we're not going to be using my complicated quantum system to exchange the message. We're going to use this system to exchange the secret keys. And when we know we've done that securely, we're going to use the one-time pad, which is lovely and simple and mathematically secure, to exchange the actual message. Okay, right. That was cryptography. Now it's getting quantum again. What we have is Alice trying to exchange a secret key with Bob, and she's going to be sending the information on single photons. And we know from one of the basic tenets of quantum physics is that performing a measurement on a quantum system changes, perturbs, alters the system. Okay, so here is Alice sending her message to Bob in the form of blue photons on my screen. And when Eve, the eavesdropper, comes along, she can take the photon, she can measure the information on the photon, but she changes the photon in so doing. And that means that Bob can spot her, okay? So it's not about being able to always exchange the information securely. We're not sending the secret information. We're sending the secret key, and we're using the fact that we're doing it on quantum particles to mean that we can always detect eavesdropping because of this fact that measuring a quantum system changes that system. Okay, so next question might be, well, how do you send information on a single photon? And this is where the fact that I said before, my single photon sources emit polarized light starts to matter. Because how we send the information is we put the information on the polarization state of the photon. We put the information on which way the electric field in that wave that is the light wobbles, okay? That forces Eve to take measurements that we can spot her making, because there are some that she could sneak in that we might not notice. So this is what we do. This is the BB84 protocol. Again, two guys whose names began with B invented this in 1984. We have two ways of putting information on our photons. We have the rectilinear basis, in which the vertically polarized photon is a 0 and the horizontally polarized photon is a 1. And we have the diagonal basis, in which the kind of forward-leaning photon, the positive 45-degree photon, is the 0, and the back-leaning photon, the minus 45 degrees, is a 1. And we can send information using either of those ways of thinking, either horizontal vertical, or positive 45 degrees, negative 45 degrees. Okay, so he's going to transmit as 0. And she's going to pick a basis in which to transmit, literally at random. She's going to effectively toss a coin and say, right, this is she's using. She's going to use a polarizing filter or my polarized single photon source, which would be more efficient, to polarize her photon and send it to Bob. Okay, now here's Bob. He does not know what basis she used. He can use a calcite crystal and a couple of single photon detectors to measure the polarization of the photon, but he needs to know the basis, and all he can do is guess. So he guesses, and he might get it wrong. If he gets it wrong, what he's going to measure for this plus 45-degree polarized photon is either horizontal or vertical, 50% probability of each. So what data he gets out, if he guesses wrong, is a coin toss. If he gets it right, he will measure the correct polarization. Okay. Now, that means that half the time he's going to have guessed wrong, and half the time his data is just totally random, not useful at all. But how we deal with that is that after we've finished sending the key, and after it can no longer be eavesdropped on because the whole sending of it is all done with, then Alice rings up Bob, and not worrying about privacy, not worrying about anything else about being eavesdropping, explains all the way through what basis she used. And they figure out where they matched, and they just check out all the data where they didn't match. They don't discuss the data, they only discuss the key. Okay, so this is how it might look here. But trying to send, and let's say he finds you perfectly well, and then later, much later, they come along and they find they did indeed use the same basis, and they keep the 0. Yeah, Alice is trying to send a 1, and she uses the rectilinear basis. Bob measures in the diagonal basis, and he gets a 0. And when they discuss, they say, oh, our basis didn't match, and they just chuck out that one. It'll happen occasionally, let me find one in my table, that Alice sends a 0 in the diagonal basis. Bob uses a different basis, but because it is just a coin toss what data he gets a 0 as well. But they don't know that. They don't know that they match because they can't discuss the actual key. They're only discussing the basis. So even though they happen to match, they're checking that data as well. They only discuss the basis, not the data, and they only keep the data where the basis matches, which here is just 4 numbers. Okay? Those ones have all been chucked out. Now, what happens when we introduce our eavesdropper? Again, Alice is trying to send her photon, and Eve is going to intercept it. Now, if she wants to know what information is on that photon, she has to take a measurement. Okay? And she, like Bob, doesn't know what the basis is because Alice hasn't told anyone. 50% of the time, she's going to get it wrong. And then again, it'll be a toss-up whether she gets a 1 or a 0. And the other half of the time, she'll get it right and she'll measure correctly that part of the data. But it doesn't matter. She's correctly stolen half the data here, but it isn't actual secret information. It's just the key. All we're trying to do is exchange the key to use to secure the information later. Then she's going to have to send a photon on to Bob. Now we know that Bob also doesn't know what basis to use and is going to be getting it wrong. But we're not going to worry about the places where he gets it wrong, because it's about the ones for which Bob happens to be using the same basis as Alice. For these photons where Eve got it wrong, she sent a whole random mixture of vertical and horizontal photons, and he's going to measure them in the diagonal basis. So half of these are going to yield the wrong bit at random. And the ones where Eve happened to pick the correct basis will arrive at Alice in the state Bob intended. Sorry, will arrive at Bob in the state Alice intended. So half of the time, all is well. Of the other half of those are right at random and half are wrong at random. So previously, in the sifted key, Alice and Bob should have been matching perfectly. But now we've brought Eve in, we have a 25% error rate. She's caused Alice and Bob to differ in the key 25% of the time. Now, we have been talking this through like one bit at a time. Actually, this is happening at, hopefully, gigahertz rates, so 1 billion data bits per second type rates, done by computers, okay? And we are sending billions of binary digits. And what we do is just send rather more than we actually need. We need our key to be the same length as our message. So we don't just send a key that is the same length as our message, we send a key that's 10% longer. And then we discuss a portion of it, again, over a public channel. We let Eve eavesdrop, because all we're doing with that extra 10% of numbers is checking whether eavesdropping happened. We're not going to use that bit at all. We're just looking for that 25% of errors that Eve will have introduced by eavesdropping. And as soon as we find the errors, we know that our key has been compromised, that it's no good to us, and that we have to find a more secure channel. So as I say, it's not that we can stop Eve from eavesdropping, but we always know if she's there. And because we're only sending the secret key, we just wait, we find a new way to send the data, and we do so in a secure way. And then we use those keys that have been exchanged to send the data, the real secret message securely. Okay, so why do we need a single photon source? This is one of my very oversimplified animations, but basically, because if we're sending lots of photons, Eve doesn't need to retransmit a photon. She can just nick one and measure it and doesn't have to send it on. And it's incredibly difficult with any light source that gives out random non-fixed numbers of photons to know how many photons you're sending, because it is just a random variable and you can't count them before you send them. So Eve can just kind of siphon off spare photons. And in fact, because the channels over which we send photons are always leaky, we always lose some photons on the way. So if she can just kind of steal one we would have lost anyway, then we're really stuck. So without single photons, Eve comes and steals one or a proportion of the photons, and we can't detect her anymore. All of this sounds like science fiction, but are people making it work? Yes, although actually, interestingly, often not using proper single photon sources as yet. They're often using very, very dim lasers, which are made so that a lot of the time they give you no photons. Most of the time they give you one photon, and there's always a finite probability of getting 2, and actually always a finite probability of getting 17 or even 96 or something. But with those kind of slightly dodgy single photon sources, they've nonetheless demonstrated this in the lab. This is a lab-based system sending the data through optical fiber, and they have, on a huge great drum wound up somewhere in the back of their lab, 307 kilometers of optical fiber, and they're transmitting data like that over those sorts of distances. Taking it out into the real world, this is a field trial that's going on in Tokyo. And they haven't quite got 307 kilometers, but they have literally strung appropriate fiber between telegraph poles. So like the telephone wires go in the kind of traditional picture of telephony, across 45 kilometers of Tokyo. And they are transmitting data in a quantum key distribution protocol at rates high enough that you could use it for secure transmission of high definition video. And they've made this to be stable over weeks. So this is genuinely workable as a communication technology. The Chinese are really doing well at doing this in space. They launched their first Chinese satellite-based QKD system in 2016. And in 2018, they demonstrated this type of quantum key distribution, this type of quantum cryptography between continents in a satellite-to-satellite based paradigm. So it is coming online out there in the real world. Okay, so I'm going to sum up. I said I was going to answer 3 questions. The first one was, well, what is light anyway? And that turns out to be a hard question. Light is a ray that travels in straight lines, but it is also at the same time both a wave and a particle. And when I've been talking about single photon sources, I've been talking about both using the particle nature of light and the fact that it is a single particle and you can't steal part of that single particle, you have to steal all of it and be detected. But I've also been simultaneously talking about using its polarization, which is the direction in which the wave is vibrating. So this kind of duality here is borne out in a potential practical application of light. How do we use this light for secure communications? We do it by using it to exchange our secret keys and always being able to detect whether we've been eavesdropped on. We can't prevent Eve from eavesdropping, and that does still give her some power over us because she can just stop us sending information, and that can be a pretty powerful thing to do. But we can always figure out that the eavesdropper is there using these types of approaches and know whether we're sending data safely. And there's an irony here, because the most likely thing, I think, which is going to break current cryptography is not really like a starving mathematician in a garret coming up with some brilliant idea. It's probably quantum computers, some of which might even use the type of single photon source technology we've been talking about. There are designs for that out there. So we're kind of the people who work on quantum science, whether at the grubby end like me, or really developing these huge systems or the theory of them, we're basically both creating and solving the problem. We're going to potentially create computers which can break the codes that we use to communicate with securely, but we're also going to use the same type of physics to solve that problem and provide a new way to do secure communication. Okay, thank you very much for listening. The science behind this, there have been lots of folk in my group and also in my collaborators group in Oxford involved in. And yeah, feel free to ask me some questions. I shall stop sharing for a second. I may put it back at some point.
Firstly, thank you so much, Rachel. That as mind-blowing as it is to consider that sort of thing, it was really, really clear, and thank you so much for that. So we'll go to questions now, if that's okay.
Yeah, go for it.
There's a couple in the chat. So we've got, does a quantum algorithm have to be written by a mathematician, or is it developed by the computer itself?
So typically they are still written essentially by programmers. I think there's a really interesting crossover between the quantum computing field where, yeah, people are still figuring out how to write quantum algorithms and what they will do with a quantum computer once they've got one. But the quantum algorithm is still very much imposed on the computer by the programmer. But there's also this whole coming picture of AI and the robot scientist and letting the robot design the experiments. And at some point there will be a crossover of those two things. And it may be actually we use a conventional computer, to an extent maybe we already do, use a conventional computer to design the quantum algorithm to run on the quantum computer. I don't think as yet we can make the quantum computer design its own algorithms, partly because it's only got 50 bits and there's only so much you can do with 50 bits.
And the other one was doing the transmission via space, so across the satellites. So does that mean that then a cable's not needed?
Yeah, exactly. So in fact, free space is a totally amazing channel as long as there's nothing like a hill or something in the way. So we tend to send this kind of photons obviously down optical fiber. An optical fiber is quite lossy. It absorbs quite a lot of the photons, and it also has what we call birefringence, which we mean the ability to change the polarization of the photons. So when I've carefully put all the information on the polarization state of the photons, if I send it down an optical fiber, it may not still be there when it gets to the other end. Free space is non-birefringent. It does not change the polarization state of the photons, and it doesn't absorb very much if you're talking about like space, as opposed to like trying to do it between Manchester and Cambridge, where there'd be like clouds and hills and aeroplanes and stuff in the way. So actually, like how many photons you lose is really important to how quickly you can transmit information. And the Chinese reckon they can do it orders of magnitude, many tens of times or hundreds of times faster using their satellite to satellite based systems than the people who are using fiber optic cables can, because there's so much less absorption. So yeah, free space is a great channel basically.
So where does that leave us in terms of transmitting between the satellites and somewhere on Earth? If that's
So yeah,
in the future.
so then you need ground to air systems, but again, almost certainly not cable based, almost certainly free space systems. The thing that becomes difficult with all of this is that, yeah, it all depends. We have to get the information out of cables and into space almost very likely at some point, and that part's hard. We need to worry about what we call quantum repeaters, things that securely repeat the signal, and that's very, very difficult, and that's a big research area, figuring out how to make that work.
Okay, thank you. And then we've got from our dear biology teacher, who is very tired today, bless him, but he wants to know if when you say grow the crystals, and I was actually wondering this as well, is it like growing salt crystals but on a smaller scale?
So there are ways, so the types of tiny crystals that I was talking about, I talk about as quantum dots, okay? And there are ways of making quantum dots that are literally like growing salt crystals, because basically how you make a salt crystal is you start off with a solution and you basically precipitate out the salt, yeah? And you can precipitate cadmium selenide out of some complicated solutions of cadmium containing and selenium containing organic solvents, very much like growing a salt crystal, but small. And the trick there is to stop them from getting bigger, which you pretty much do by adding another reagent to the solution, which covers the surfaces of the crystals. And then that stops them from growing because they're like protected all round from adding more cadmium and selenium on. That's not how I grow my crystals. I grow my crystals from a vapor phase, which actually, I can remember doing experiments at school with like evaporating iodine and ending with crystals of iodine on a cold finger. I don't know if anyone's ever seen that one. But basically we put in the gas phase, we put the ingredients for our crystal, and then we provide them with a surface to land on at the right temperature to form the crystal, and the atoms move around on the surface until they get into exactly the right place to organize into a crystal, and the crystal expands by dint of adding these atoms on. So the reason we're talking about growing the crystals is we give it the gases it needs and the crystal gets bigger, it grows. So like, it's not quite like growing daisies, but along the same lines. Does that help?
Yeah, definitely. So Paul's asked, how commercially viable is this form of communication, or is it sort of cost prohibitive? He's thinking next generation secure messaging and emails. So
probably not next generation, but it's coming your way, I would say. So the systems, the thing that I kind of work on and am most interested in is systems that work at accessible temperatures. So single photon sources and single photon detectors 10 years ago, depends a bit on the color of light you're working with, but probably both of those would have needed liquid helium, okay? These days, the sources, at least for my materials, we can get them working at close enough to room temperature that you wouldn't know about the cooling. And there are very, very good detectors that I know of that are being commercialized, but it's all quite secret, that equally will not need very much cooling and will be efficient enough to do this. So from that point of view, the costs, when you take away the liquid helium, the costs are coming down quite nicely. The things we have to worry about are what I refer to as manufacturability. So the ability to do this at scale, make lots of these things quickly and cheaply, and with yield, by which I mean all of them work or 99% of them work, rather than what we do in the lab at this point we refer to as hero devices. Like you test 100 and number 1 and number 7 are great and the rest of them really don't do anything very useful. So there's a lot of hurdles to overcome there. That said, if you use colors of light that can use the best room temperature single photon detectors, and you're willing to use weak laser, which is not perfectly secure, you can actually buy a quantum communication system off the shelf from Toshiba right now, if you want one. And there are people in Bristol whose kind of major research direction is trying to get this pocket sized. So their picture is of something they call a quantum ATM, so a quantum cash machine. And the idea being that like we go to the cash machine to get cash, when you went to the cash machine to get cash, you'd sit your mobile phone in a little cradle and it would exchange secret keys with your bank. And that would be your supply of secret keys that would then secure your financial exchange of information for the next month, until I guess you went back to the cash machine and bunged your mobile phone in the little cradle again. And that, in terms of consumer applications rather than military, is probably where we'll first see this coming online. And I don't know, might be looking at a 10-year timescale to something affordable and manufacturable, or I might be being a bit optimistic. Not sure.
Lovely, thank you. And then we've got another one from Robert. Forgive me if I don't ask this correctly, Robert, you might want to come on and ask as well. But he asks, how would the single photon be routed through a fiber network? Would it use a separate channel of communication? And then he goes on to ask, in your PN junction emitting a single photon, does most of the depletion region, where the electrons and holes recombine, behave like a traditional diode, and only the quantum dot behaves like an LED due to the difference in materials used? Makes sense to you? Because to me, I'm a biologist and this is far beyond me.
Okay, so in terms of routing it through the fiber network, I'm not totally sure. I have to admit, I've not thought about that one before. The same fibers would be good fibers to do this with, but we can't kind of have our single photons be lost in a huge stream of, I don't know, what are we all streaming? Have I got news for you, or whatever? Yeah. So I don't know whether it's been thought out whether we can do it in the same channel, or whether we actually have to have separate channels. I'd like to say there might be a way of what's called wavelength division multiplexing, which is working in a wavelength space, so different colors for different forms of information. I have a feeling, though, that everybody's going to want the best wavelength, both the streaming of Have I Got News for You and the quantum cryptography, and I don't know how that's going to be overcome per se, but it's not something I'm actually sure about. There may be another answer to that question. On the really technical one, so my PN junction, does most of the depletion region act like a traditional diode? Yes, it will, except that probably we're injecting so few electrons and holes that very few of them will actually kind of encounter one another in that region of the diode. But yeah, we will get a leakage current, which is recombination away from the quantum dot. Actually, we will also have other light emitting recombination channels are quite likely to be present. We only care about the light emitted at the specific wavelength of the source. And another part of the architecture of our device would be a notch filter, which would filter out all the other colors. So it could be that actually the whole thing's acting like a normal LED, but at usually slightly shorter wavelength. And we use the slightly longer wavelength, the slightly more towards the red photon for our quantum communication. It depends exactly on how you make your quantum dots. Does that help?
Very good answer, thanks. You've helped a lot.
Cool, right. Anyone else? I'm quite happy if people just shout out or to send them through Stevie in the chat, whichever suits.
Now, if anyone's got any other questions, please unmute yourselves and ask away. If not, could everyone please unmute now, and we'll give Rachel a big round of applause for her talk this evening.